I will already start the introduction. Next, we will have Andreas Ruckstuhl and Kurt Stockinger talking about what we learned about the data science life cycle, and we will learn best practices and remaining open research challenges. Just looking at your name tags. Andreas, you're a professor of statistical data analysis at University of Applied Sciences in Winterthur.
Yes.
And Kurt Stockinger, you're a professor of computer science, and you're also involved with the data lab at your university. And now we look very much forward to your talk today.
Thank you very much.
So hello everybody. I do first a little introduction, so we'll tell you a little bit about what we learned about the data science lifecycle, and we give you two different perspectives. One from Andreas Ruckstuhl, from the statistician's perspective, and from my perspective as a computer scientist. And we will first show you a little bit about the data science lifecycle, what it actually means, and then we show you a few of the research projects that we have done, show the good stuff, but then we also show what are still the open research issues and where we as a community actually can contribute.
Yeah, thank you very much, Kurt. But first, before we start to this main issue, I would like to introduce first the data lab. It has been established in 2013 as an interdisciplinary data science initiative at Zurich University of Applied Sciences, and it is one of the first in Europe. The most prominent outputs of it are this. Oh, excuse me, that's the wrong side. Here, that doesn't work. It is actually the foundation of the Swiss Data Science Conference in 2014. And another thing is that there is a well-established postgraduate program, Master of Advanced Studies in Data Science in Winterthur. And the third prominent part is this book, Applied Data Science. And currently the data lab is headed by Robert Vorburger and Kurt, my colleague here. So that is our data lab. It's interdisciplinary. This covers the whole Zurich University of Applied Sciences. So, but now to the phases of a data analysis. Well, this is a thing that has been looked at since a long time, and also how it should be linked between the different phases. Daniel and Wood, for example, have put the phases into a flowchart in their 1971 book, Fitting Equation to Data. Then, in the age of data mining, a data analysis process was formulated around 2000 called the Cross-Industry Standard Process for Data Mining, which is still very influential today. And even today, in this age of data science, the phases can be found again, such as in the team data science process lifecycle of Microsoft in 2017. The essential elements remain the same. They have only become, as you see here, more colorful. These are business understanding and the goal of the whole project, data acquisition and data understanding, modeling and evaluation, and finally, deployment. Today, I want to focus more on the analysis phases than on the process, the fixed process itself. So it is not, we don't talk about all this understanding, but what I have to say is some characteristics. These individual phases well, it was always clear that the individual phases were part of a very complex iterative process. During the analysis, one will go through these phases several times. Each step will incorporate the knowledge already gathered. And also, what has to be done in the final phase, in deployment, depends on the goal. And vice versa, the goal of the analysis is influenced by the possibilities in deploying the result. So, for example, in one of the modules in the Master of Advanced Studies in Data Science, the postgraduate students develop an analysis concept according to the CRISP-DM. Part of the work consists of looking at some details more concretely, such as whether the data actually are suitable, which model procedure should be used for the analysis, what requirements must be placed on the performance of the model so that the goal can be achieved and the approach can be deployed. This task quickly shows the students that the whole thing is not an easy process to work through, and some iterations are necessary even in setting up the concept. And if you go through the whole issue later, you have to do it even more, in more consequence. Well, some of my experience come from analyzing insurance claims. What becomes clear again and again is that you can also improve data quality and business process understanding by analyzing the data. For example, it was only when analyzing the data that it became apparent that at a certain point in time, administrative costs were also included in the claim costs. The business process owner knew about it, but it was not recorded in the data warehouse. So, in order to obtain a meaningful analysis result, the definition of claim cost has to be standardized. So what we did is we removed these administrative costs, did modeling, and later in a separate part we added these administrative costs again. Another quality problem arose because a certain business process was not implemented as intended. Also, the data cells in the data warehouse did not contain unusual values or unexpected things. The values did not match the intended definitions for some variables. So as a result, the process was adjusted so that the data was recorded as intended. And for us, the result was that the affected variables cannot be used for analysis. I think it is very satisfying to learn how the business process works based on the data analysis, and to be able to confirm either that it is working as intended or that there are problems in this process or in the recording of the data. So usually use your data and you can improve its quality. So, and finally, if your data science products are based on business processes, be aware that business processes are subject to constant change. This is a consequence of the guiding principle of continuous process improvement. However, continuous process improvement also means that data acquisition can change, and thus the data warehouse or the data mart must keep up with this dynamic. When modeling, it must be taken into account that variable can contain stationary breaks. That is, at a certain point in time, affected variable no longer contain the same values in terms of content, and consequently the same relationship between the variables no longer needs to exist. So that will cause problems in the predicting capabilities of every model. So continuous process improvement is necessary and useful for business, but is a big challenge for data science. And now another challenge for Data science will present Kurt.
Good. Now we switch gears slightly. So we now saw the data life science cycle, and now we want to see how can we analyze data. And one of the most obvious ways of how we talk to human is we talk to each other, right? So if you have a question, you ask something, and you hopefully get an answer back. And if the person you're talking to doesn't understand, the person also says, I don't understand. My kids, for instance, if they don't understand what I ask them, they start crying. Maybe that's not the best idea, but at least you want something to talk to your data and talk back. And this is the vision that we also have, that we want to have in the whole data science lifecycle, right? And why is this important? Because how do you currently access data? And typically, this is done for some experts, right? If you know SQL and you have a relational database, you can query everything, right? If you have a graph database and you know Sparkle, which is the equivalent of a query language for graph databases, you also can query. How many people of you do know this? Maybe not too many, right? So first, you need to understand the data models. So how is the database structured and so on. If you have different data, let's say relational databases, graph databases, or text documents, you also need to understand the APIs. It's a learning curve. Or if you want to do some more complicated stuff in data science, maybe you need to understand the machine learning technology. And this is another model, right? So machine learning model, data model, you need to understand all this. It's pretty complex, and many people here are smart data scientists, but not everyone is a data scientist out there. We're not building tools for ourselves, we're building it for the non-data scientists, maybe. So basically, the idea is that we need to talk to the data similar to the humans, and if the system doesn't understand, it needs to ask something back. If you now have a relational database and you write a SQL statement, and it doesn't work, the database tells you error. That's great, right? So what is the next step, right? So we need some kind of intelligent system that helps us a little bit to analyze the data that we have in a quite intuitive way. I give an example of how you currently would query a graph database. And graph databases are important because they're used in the life science community quite a bit. And life science is today a medical area, so a lot of data is in graph databases. And let's assume they had one question like this. What are the drugs for diseases associated with a BRCA genes? As a doctor, you might know BRCA stands for breast cancer gene. Okay, so you can ask the same thing for genes that are associated with lung cancer, whatever. Then you have the COVID case again, which I don't want to discuss now, right? Now, how would you query this kind of data? With a query language called Sparkle. Question to the audience, who speaks Sparkle? One. It's good, 1.5. The people outside, I don't hear you, but maybe you can type in how many speak Sparkle and how are very proficient in Sparkle. I would say a very small percentage. Maybe my colleague, database colleague who talks in the afternoon, Joe Hellerstein from UC Berkeley, speaks Sparkle, but maybe not too many. So how does a question look like? Like this, right? Select distinct question mark, disease, blah, 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 then a few lines, and that's the answer. Quite simple, right? You would have all come up with this question or with its answer to the question. Not even the database. I tell you, in the database world, even a small percentage of people only speaks this. But this is what you need to know in order to query databases in life sciences. Hardly anyone knows this. Imagine a medical doctor who does an operation needs to know this. I think they will say, I don't care. You want to have something more like this. And this is a system that we have built at Zurich University of Applied Sciences together with the Swiss Bioinformatics Institute. So these are the guys that produce the protein database, a very famous worldwide used protein database. So we can type in here the natural language question. And then what we do with a certain algorithm, we translate it back. So you want an answer, and the answer is a table like this, right? So what do we see in here? What are the drugs for diseases associated with breast cancer genes? Here, there is a breast cancer gene, BRCA2. It is associated with breast cancer, and what is the drug? Flutamide. Maybe some of you know. I have no idea what it is, but could be an answer, right? So good, the system gave me an answer. If you look a little bit closer, same gene, breast cancer gene, the same medication, drugs, prostate cancer. That's actually interesting. I looked for breast cancer. Is it now a problem in the data? Is it a problem in the system? So apparently, the drugs associated with this breast cancer gene, you can use it for breast cancer, so for 1/2, hopefully, of the population, plus also for prostate cancer. Is it a true answer? I have no idea. The system gives me this. At least it gives me an answer. I didn't have to write a complicated query before. So just to tell you a little bit what we did in this game. So what we've built these kind of clever systems that talk to a data already over the last 10 years. And we started this off when I was still working in one of these major Swiss banks. That's why I said future ZHW employee. And we built it together with our colleagues from ETH Zurich. And we had this large data warehouse. This was during the financial crisis. And we wanted to find everyone of these nice customers who had something related with the Lehman Brothers. If you remember, this was the crisis before COVID. It was very difficult to do because the businesses had to do questions something like this, maybe a little bit less complicated, but like this. And you can imagine it was not very efficient because which banker knows these kind of things? So we started building this. Then we said, okay, when we can query banking data, we can go a little step further. We want to query bioinformatics data. More complicated, more structure, and so on. Then we said, okay, we worked with a Zurich startup called Visu that did something similar, and we extended it. The difference is now that we can not only translate a natural language question to SQL or to Sparkle or to a database language with, in the beginning we used pattern-based approaches. Now, guess what we're using? Neural networks, transformer, all the latest, greatest stuff. But now what we say, we don't only want to talk to databases, we want to also talk to machine learning models in natural language. So give me all the customers that I should recommend this product. So product recommendation is machine learning algorithm, and then you embed it into the system. So you have a dialogue, not only to a database, but also to machine learning. Here we basically started, but it's a very interesting journey. And then since we trained within Switzerland quite a bit, we said the next step is to bring this to the European Union level. And there we have currently this project, which is called INODE. It stands for Intelligent Open Data Exploration. And we're building this together with 9 partners in Europe. One of them is the Max Planck Institute. They got the Nobel Prize in physics last year, so we're lucky to work with a Nobel Prize-winning institute. Fraunhofer, French Academy of Sciences, and so on. And there we even go a step further, that we say, assume that we don't only want to have graph databases or relational databases, we also want to query text. So how can we query all this together? So this is what we're doing in this INODE project. Here's the web page if you want to look. We're always interested in having partners, and we get brownie points if we have more partners coming up. So here the idea is go a bit further, not only natural language questions to graph databases, relational, but also to text, and help the user guide. So if I ask a question, the system guides me in the right direction. So for instance, the use case that we have, we're looking at the sky. So we have astrophysics use cases, and we're looking at some specific interest in the sky, where the galaxy formation, that tell us, well, here's an interesting spot in the data. Why don't you look in there? And again, with natural language dialogue, but also with analytics, user interfaces, and visual interfaces. Okay? So once we build these systems, then let's assume the systems are okay, and they work quite well. The question is, and this hopefully leads to some interesting discussions afterwards, there's the race between artificial intelligence and human non-intelligence. So building this system is great. Over the last years, we tried all kinds of things, different domains, banking, biology, astrophysics, cancer research, different technology, neural networks from pattern-based system. It's really fun to build this, and you learn quite a bit. We kind of consider we're doing something similar, like Google, but different. Once we have this, we can understand data faster, and we can also maybe understand our business faster. The only problem is what happens to us humans. So now we assume AI provides the answer to everything. I ask a question, the system gives me the answer back. But does the system really explain me the answer? I did not get any explanation why the breast cancer gene is also associated to prostate cancers. Is this a data quality problem? Is it an algorithmic problem? So do we just accept the answers? Or how do we understand that the system is not giving a random answer? And this is something which I think we need to be aware of, that we can build smart systems, and it's great, but we also need to understand them. Otherwise, we as humans, we just take an answer, and we cannot even explain it anymore, or we cannot even understand it anymore. That's a big challenge that we have so far. But it's an interesting journey, and I think here is still quite a bit to do. Summary, what did we tell you today? So we basically told you that data analysis process is, you don't do just data analysis in the very end, you do it over the whole life cycle, right? You get data, you clean the data, you process the data, you analyze, And then you want to talk to your data basically in all these steps. And the interesting thing, these things go together. And then, if you do this, then you will also maybe solve the data quality problem, something which I always say, almost every company, almost every institution has some data quality problems. No one wants to deal with it. It's basically the unsexy problem, I always say. But why don't we use sexy technology like machine learning to solve data quality issues, right? So then you do something cool for something useful, because this is something which really hurts us, right? Data quality problems. Why is BCR gene related to prostate cancer? And then the interesting thing is, and this is for the data science community, we've developed quite a few interesting things, but we still need good data scientists. We need skills. So data scientists will be here, even if the interfaces are smart. In the end, they will not be used by the business people because they don't have time. In the end, even though we try to build these smart interfaces for the business, or let's say for the higher rank, in the end, it's the data scientists in the end who have to do this. So this means data science will even become more important, because we are the only ones who hopefully understand a little bit how the systems are and give the explanation maybe to the others who make actually the decisions. Okay? And if you want to know more, you can read a few stories at night in our applied data science book.
Kurt, Andreas, thank you very much for your inspiring presentation. I now learned more about the race of your systems versus human non-intelligence, and hope you will win. May I now ask the audience offline and online to post their questions either in the microphone or in the chat? Yes, please. The microphone, please, so the online viewers can listen as well.
I would say I have an industrial question. All these interfaces you just showed us to query databases in natural language, are they available, or how is their state?
So let's say when we started 10 years ago, we were pretty alone on this planet. Microsoft did a little bit, IBM did a little bit, and we basically had this crazy idea to do it, and we were lucky that we got funding for it. Now it's quite a race. Google has something, Microsoft, all the big players have something. If you look, let's say Microsoft, there's Power BI, Power Business Intelligence, they're doing something similar. And there's a colleague from ZHW who's also here, Mark Chirlibach. Even the natural language processing community is now interested in databases. So this means all these guys that could care less about databases before, but you have a lot of data in databases. So there's really an arms race. There's an international competition called the Spider Challenge. I looked yesterday, who are the leaders there? Before it was Microsoft, Google, Facebook. Now the current leader, I think Tel Aviv University with the Allen Institute of Artificial Intelligence. So there's a huge, now it's a huge interest, which 2 years ago it didn't really exist. So it's incredible. Are the systems available? Part of them. Do the work? Good enough. Are they perfect? No. So that's why we're here, and that's why we can build something. What is interesting, it's not a new field. I used to work in the US for a few years, and I showed the system to my boss then in the US. That was a few years ago, and he said, "Wow, you're working on the system?" He said he worked on the same problem in the 60s, and I showed him what we have achieved 40 years afterwards, and he said he was really impressed. Is it perfect? Not really. In comparison to what they did or what has been going on for the last 70 years, it's quite impressive. But yeah, it's still a lot of things to do. That's good. So we will not be unemployed.
More questions? Georg, online also not? Then I may thank you for your inspiring talk.
Thank you.
Andreas, thank you very much.